So last time we saw that for equal time, correlation functions at temperature, that's the trace of my operators with the thermal density matrix. And we expanded the thermal density matrix out as a path integral because this density matrix has no I in here. The path integral looks like the path integral in Euclidean or imaginary time. Okay, which we should not yet confuse with actually time. It's just a parameter to keep track of this exponential. And the operators so far have to sit at equal imaginary time. And so this then had path integral representation in terms of my fields, which just, when I don't know what else to do, I'll write them as if they're all scalars for simplicity. And these fields live in space times an interval. And this is our Euclidean time, and this is our normal space. And then I have exp minus integral from 0 to beta d t Euclidean d3x. Euclidean Euclidean action density, and then my operators. With a 1 over, no, sorry, this is my partition function. If I put the operators here, I'm trying to evaluate an expectation value, and then I have to write 1 over the partition function, where the partition function is this thing without the operators. If I have this thing without the operators, I have everything I need. If I've inserted an external source that I can vary to put in whatever operator I want. And what we saw is that the perturbation theory is not quite the usual perturbation theory, but the usual Euclidean perturbation theory. That is, after Wick rotation, if you spend your life in Minkowski space, but the big difference was that integrals over frequencies were replaced, because this is a compact range, with discrete sums. So the first thing we have to figure out is, what does that do? How different is my life with these discrete sums? So to give an example, I'll consider free scalar theory. And I'll just ask about the expectation value of phi of x, phi of 0. That's just a Fourier transform of this propagator. And I'll do this at mass equals 0. To make so it's the free massless, simplest theory you can imagine. Okay. In vacuum, we know the story. You get an integral. It's just a Fourier transform I'll call that z of 1 over p squared. And after a little work, you find that this is 1 over 4 pi squared z squared. So it has this characteristic 1 over z squared singularity, and at large distance is a tail. Okay? Thermal, I need to do a sum on the P0. And if for fun, I renamed this m squared, then that would look just like a massive correlation function in 3 dimensions with then a sum over a bunch of different choices for what the mass should be. Okay? This correlation function, I mean, it's also a little bit of work, but it's not actually super hard. You get still this T sum. And this correlation function is, as most massive things, is a function in space, something that's exponentially decaying. And you can see that quickly by first doing the PZ integral. You have this oscillating phase, and then you have something which has a pole at imaginary PZ. At PZ equals I times P0. You pick up that pole with your contour, and this turns into an exponential suppression. And so you find here T from, oh, I have the T already there, 1 over 4 pi z e to the minus z times the mass, which is now P0. This is an infinite series. Before we calculate the infinite series, let's contemplate it for a moment. Each term in the series behaves as 1 over z instead of 1 over z squared, as here. The most important term is the term where P0 is 0. This is missing. I only have that. That term has a weaker behavior here. It's still divergent, but weaker. And a larger behavior here. Okay? Because it's 1 over z instead of 1 over z squared, at large z's it's bigger. Then I have a whole bunch of things that look very similar, but with exponential fall off. And I need to add those all up. At large distances, only the P0 term matters. The other ones are all gone. They're all exponentially suppressed. At short distances, they're all piling up. So we do the sum. I mean, it's not that hard. And we find that this is T over 4 pi z, hyperbolic cotangent of pi tz. Hyperbolic cotangent you only deal with once every 2 or 3 days, not every day. And so you have to be reminded of the different behaviors. At large values, this goes to 1. So at large z, we get T over 4 pi z. That's bigger than this because it's missing a pi and it's missing a z. So there's a scale here which is roughly z is 1 over pi t, where it switches over to being significantly larger. At small z, cotangent hyperbolic goes as 1 over its argument, And so I have to put a 1 over pi tz down here. The t undoes that t. The z joins that t, z, the pi joins that pi, and I get 1 over 4 pi squared z squared. What do you know? It's exactly the same as this behavior. So the short distance behavior is the same as in the vacuum. The long distance behavior is very different. Okay? The fact that the short distance behavior is the same as in the vacuum, well, that's partly because if z is very, very small, then lots of p's contribute here, and then the typical p is much bigger than the spacing in the sum. And then the sum is almost the same thing as an integral. How far off is it? Well, it's actually only power suppressed corrections here. If you expand this further, the next term is a constant. So these differ from each other by constant at short distance. That's still better short distance This 1 over z squared short distance behavior is what leads to renormalization in our theory. If I only shift it by a constant, that doesn't change any of the renormalization properties, any of the short distance physics of the theory. The short distance physics of the thermal theory is the same as in the vacuum theory, up to terms which have no influence on renormalization or any of the fancy stuff of short distance field theory. So if your coupling runs, it still runs in the ultraviolet. Whether it makes sense to talk about it running in the infrared is another question, which we will address. Okay, what about fermions? So for fermions, well, for one thing, I have a p slash over p squared. And then my sum is over 2n plus 1 pi t. Odd half integer multiples of 2 pi t. Or odd multiples of pi t. Okay. And after a comparable amount of work, I mean, I didn't work these out because it would take 5 minutes. If you try to do it back in your room, it will take 10 minutes because you're not used to these funny things. But it's not super hard. This can also be performed. First of all, what does it look like? So it's partly the same story here. I have here a p vector squared plus a p naught squared. This thing acts like a mass. Same as here. Except here, there was one contribution where p0 was 0, which acted massless and lasted forever. And the others all acted massive and fell away. Here, p0 is never 0. So while in vacuum, I get something that behaves like that, at temperature, I get something that behaves that it always has an exponential tail. Every term here has an exponential tail. So the answer turns out to be gamma dot x over 4 pi, oh, I called it z, well, whatever. Then let's call it gamma z, z over 4 pi z cubed times minus sinh pi tz minus pi tz cosh pi tz over sinh squared. Whose limiting behaviors are the vacuum behavior at small z and e to the minus pi t behavior at large z. So at large distance, this thing decays exponentially. That's good news, actually. It means that at weak coupling, actually probably at every coupling, in a finite temperature system, there's no physics of fermions propagating long distances. They don't. They only go short distances. However, the bosons have much larger correlations at long distance than we're used to. This simple example illustrates a general feature. Whenever we have, okay, so one thing that can happen is that you go to high temperatures, your theory either has large masses or large couplings, like QCD does over some significant range of temperatures. And unless you're close to a phase transition and something funny happens, then typically all of your correlation functions fall rather quickly. And you have very little long distance physics. Okay? Or, if your coupling is relatively small and your particles are massless or light, you can have these tails and have long distance physics. But it's only going to be bosonic physics. And that's what we want to try to understand next. So, from the point of view of somebody who's used to compact dimensions, just lives half of their day with 10 space-time dimensions, 6 of which are really small, you look at this sequence here and you immediately say, oh, I see. We're living in 3 dimensions with a hierarchy of massive particles. One of them is massive, the rest are very heavy. The lightest here is pi t. The lightest here is 0, but the next lightest is 2 pi t. If I'm interested in physics below that scale, they're all heavy. They can't do anything other than indirectly influence the ones that I want. And so I'm going to integrate them out. So let's take out this. So I can feel free to integrate out the P0 non-zero modes. What does my theory now look like? So let's do this in a concrete specific theory, actually 2 discrete concrete specific theories. Here's phi to the 4th theory. So if you only have scalars, and here's QCD. So in phi to the 4th theory, my original Lagrangian was gradients, self-interactions, and masses. And just to make life easy and fun, I'll consider the case where the masses weren't there. For QCD, I have my Maxwell Lagrangian field strength squared, and I could have various fermions. But now I want to write down, so that's what I start with, but in 3D. So this is the 4D version. But in 3D, only the fields which are bosons survive. So in 3D, my Lagrangian is a function of AI and A0. Or for a scalar, It's a function only of my scalar field. So this is the normal thing. Here I have to be a little bit careful. My field has 4 components, 3 space and 1 time. Because time is playing a fundamentally different role here, I'm going to separate out that component because it doesn't have to behave the same way as the other ones do. It can do something different. You might say, well, I shouldn't leave it in at all because it's the field to tell how things should transform as I move in this compact direction. But you'd be wrong. If you can't just leave it out, it's part of the physics. It can, even if it's uniform in this direction, it can still do something. It can still carry physics. So it has to be in here. What can this Lagrangian look like? Anything I can write for a 3-dimensional theory with this field content. Okay, so here I can write del I phi plus lambda 3 over 24 phi cubed plus m3 squared over 2 phi squared. Wait a minute. Okay, this makes perfect sense. Instead of having 4 derivatives, I have 3 because I lost my time derivative. What about variations in that missing time direction? Well, here we specified that we're only treating the modes which don't vary in that direction. So that's fine. So this is just what you would expect from here. This is what you would expect if I had written it correctly. But I'm nervous. So I'm not assuming that this lambda is the same as this lambda. Maybe it is, maybe it isn't. I'm going to hedge my bets. I'm also writing a mass term. This didn't have a mass term. I'm writing one again. Why? Because I don't know what's going to happen here, so I need to write everything that might happen and then figure out what really does happen. So just to be conservative, I should write this term. Okay? I don't have to write anything else because renormalizable theory, don't expect anything else. Actually, at the renormalizable level, it could also have a phi to the 6th. And it does, and it's super small, and I'm going to ignore it. Over here, what can I write? 1 over 4 g3 squared Fij. That's like the baby version of this. Except that's the baby version of the magnetic part of this. Remember, this is magnetic squared plus electric squared. What happened to that electric part? Well, it's here too. dI A0, dI A0. That could be there as well. The fermions, what about the fermions? They're gone. They're gone because they only had, oh, I've erased it, non-zero frequencies. So forget about them. But this isn't the only thing I could write. This theory has a 3-dimensional gauge invariance. As far as that 3-dimensional gauge invariance is concerned, this A0 is just some scalar field. Scalar fields, nothing stops them from having masses. Nothing stops them from having I guess this should be an 8. Self-interactions. I don't know of any reason those couldn't be there, so I'm going to write them. Maybe they turn out to be 0, maybe they don't. They don't, actually. For SU2 and SU3, this is the only self-interaction that can happen. For SU4 and higher, there are additional structures you have to write here. So if you like grand unified theories and that's what you study, then you have to go and look at the paper by Artur Rajanti, who worked out what you're supposed to do for SU5 back in the late 90s. But I won't do that here. Okay? So this theory could be a little bit more complicated than we expected.
Can I ask?
Yes.
The coupling constant affects both the magnetic and the electric part, no?
So I rescaled it out of this one, which then shows up in the scalings of these things. Should I have done that? Yes. I didn't have to. I could have put it here and then it would show up in funny places other places. But it's more convenient to normalize your scalar fields canonically. It's actually often not convenient to normalize your gauge fields canonically, especially when the gauge coupling then runs with scale and things like that. Although here, it doesn't run with scale. Oh, we'll come to that. I'm getting ahead of myself. Okay. Yes?
Yeah, so I'm trying to understand why it is okay to neglect the D0 phi squared. Because it's true that you're working with low energies, but...
So you want me to put a D0 phi squared here? Okay. But this is a three-dimensional theory. What does that mean?
What, the energy of the mode? I mean...
Is that different than this? But anyway, it's a mode. I'm only keeping the P0 equals 0 mode here. That's precisely the mode where that derivative is 0. So if I wanted to keep other modes for some reason, which would not actually be consistent, but I could try. I mean, if I keep one of these modes, higher modes, then I have to keep the next one because it's only a factor of 2 different. It's not a parametric separation, etc. And if I do that for some reason, then I just have to give them masses. Because since they're Fourier modes, that's what they, or if I Fourier transform in the time direction, then those derivatives turn into masses. Okay, good. Okay, so this is the descendant of the time component of the gauge field. And because in this three-dimensional picture it doesn't have its own gauge invariance to keep track of, nothing forbids it from having these interactions. They might be there. They are there. But they're only generated at the loop level because they're absent in the Lagrangian up here. Just because something is absent up here doesn't mean it's absent up here. It means that it has to arise at the loop level down here. So these things at minimum will have g squareds attached to them. Okay. Is there a procedure? What should I choose for these coefficients? Just choose anything I want? Have I no idea what to do? At this point, to determine these coefficients, I have to calculate something. I calculate some things in the 4D original and the 3D reduced theory. And then I pick the coefficients so that the answers are the same. This is called matching. If I have a complete theory here, and if the reduced theory which works at low energies, and I want to know what are the coefficients of the reduced theory at low energies, then I calculate some stuff, and I insist that I get the same answer in each one. So for instance, if you have QCD at a scale of 10 GeV, and you want to do QCD at a scale of 2 GeV. In between, there's this bottom quark mass. So in 10 GeV, you have to leave in the bottom quark. At 2 GeV, you should throw it out. It's too heavy, it can't ever appear. There are different theories. They have different numbers of quarks. How do you know how to relate the couplings of the two things? Well, you calculate a couple of infrared things in the full theory and in the reduced theory. And then you say, let's choose the coefficients of the reduced theory so it gets the right answers. With those values, it will continue to get the right answers for everything else. You have to look at the theory and count parameters. Every parameter is something you have to calculate. So I have a coupling. This is a canonical normalization. I don't have to do anything. I have a mass. I have a self-coupling. Here I have a self-coupling, and a mass. That means that here I have to calculate three things. Here I have to calculate two things. I calculate three things here. And in this theory and in this theory, I force their answers to be the same. The only way to make their answers the same are to pick particular values of these three coefficients. With those values picked, a fourth, fifth, sixth thing I calculate here and here will all agree already without my having to do anything, provided I work to the same loop order. Okay? Because the infrared behavior of this theory is the same as the infrared behavior of this theory. It has the same infrared stuff happening. And so once I've calculated enough things to know how to write this theory, then I have the right infrared description, and it'll be right for everything. So I only have to use this to calculate three things, and then I can forget about it and continue working in this theory. Or that's true until I want to, well, it'll be true for a while. Okay, why would I want to do this? Well, calculating in here is hard. You have these sum integrals. The sum integrals turn out to be difficult. And so the fewer of them I have to do, the happier I will be. If every single thing I want to know, I have to do tons of sum integrals, I'm going to go crazy. Okay? And it turns out that this theory, well, maybe I should not get ahead of myself. It turns out that this theory has its own complications. And I want to deal with those complications in the simplest setting that I can. Okay, and here I should remark that this matching has been done, and it's been done to some obscene loop order. So due to the persistence of Finnish people. So all this guy's friends, Kajanti, I'll just say et al., but it's Leine, Rumakainen, and Shaposhnikov. One Russian snuck in there somehow. He'll be here übernächste Woche, the week after next, right? Okay, so you can ask him all about this. NPB 503, page 357, 1997. And I suspect that most of the real difficult part was done by Mikko Leine, but who knows. And then Leine and Schröder extended this in 2005. And what they did is they calculated the propagator, which gives you the k squared, the self-energy, which gives you the m squared, the self-energy at the loop level, which gives you m squared. So here it turns out that the mass is of order g squared. There are further corrections which are of order g to the fourth. You have to calculate some gauge self-interactions to get the gauge coupling, and so on. And this they did at 2 loops, I think 1 loop. So they're all known to high precision. The answers look kind of funny. Because a three-dimensional theory is a weird thing. remember, up here, this Euclidean Lagrangian density has units of energy to the fourth. That's because I'm going to integrate it d4x. And I want to get something I can put in an exponential, which means something with no units. So it has to be e to the fourth. The gauge field in the sensible normalization is a 1 over length, and so this is already e to the 4. Just like it's supposed to be. And so this is dimensionless. Similarly here, this is energy, 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 so that I get up to e to the fourth. And then this is energy to the fourth. So this is energy to the 0. Energy squared, energy squared. But down here, this is still e to the fourth. But this is supposed to be e cubed, because I want to integrate it over space, 3-dimensional space. And that means that this thing in the denominator has to have units of energy, not dimensionless anymore. That's weird. So g3 squared is g4 squared times t times corrections. Which, roughly speaking, are that this is renormalization point dependent. This isn't. This is a number. Well, times t. The renormalization point dependence is more or less fixed by setting mu equal to pi t. That's not quite exactly true. There's a e to the, I think there's a 4 and an e to the minus Euler constant and stuff like that. But this is true up to constants. And then they even found it at 2 loops, if you want to worry about that. This m squared, md squared, arises as a loop effect. It vanishes in 4 dimensions. So it arises from this loop only because this loop is sum integrals instead of integrals. So because the scale of temperature is sitting there in that loop. And so it has to go as g squared t squared. Its energy units get made up by the temperature. It has g's because it comes from a loop. And then it has some numerical coefficient which has to do with the representations and stuff like that. This is for fundamental fermions. So the fermions play a role. They help choose the coefficients of this theory. And once they've done that, you're done with them. You never have to touch them again. Okay. And this lambda is of order g4d to the 4th t. At weak coupling, it's very small. At larger coupling, it might not be so small, because it has to arrive at the loop level, and it's a 4-point interaction. So it has to arise from sort of loop things where you have g squared twice. Similarly, over on the scalar side, this mass squared, yes? Here. Right. Ah. So if I want to write this with a coefficient of 1/2, I have to absorb a square root of t into my definition of A0. So this has dimension energy, and this is energy to the 1/2. I should have said that. It's the same story over here. This is energy cubed. The derivatives are each an energy, and so the scalar has to be an energy to the 1/2. So this scalar phi 3d is phi 4d over root temperature. This then has an energy squared, and lambda has to have units of energy. This has units, since it's E squared, of energy, and the mass squared has units of energy squared. And similarly, this is energy squared, and this is energy, and so this is energy squared, and this is energy. Yeah, so there's some funny adjustments to the units. Some various powers of t and square root of t when you go from 4D to 3D. That's actually interesting because in 3D, imagine I were trying to calculate the renormalization of this thing in the 3D theory. It doesn't normalize. Calculate a loop correction. So if I have some process, I don't know, some scattering process, which is G3 squared, and then I calculate this correction, that'll be a G3 to the 4th times some integrals. This has units of temperature. This is units of temperature squared. So this integral has to have units of 1 over temperature or 1 over momentum. And that means that if the momentum is large, then this is a suppressed correction. So if you go in deep into the ultraviolet in this 3D theory, loop corrections are suppressed. This does not shift the value of this thing. The thing doesn't renormalize. In 3 dimensions, gauge theories are not just asymptotically free, they're super renormalizable. The coupling has a value, period. That's great. It actually, among other things, means doing this theory on the lattice is way easier than the 4D theory. First of all, you only have to simulate 3 dimensions. Whew. Second, the finer you make your lattice rapidly as a power, your coupling gets smaller and smaller, life gets better and better. Third, no fermions. That means that whereas lattice QCD in 4 dimensions is still an active field of research, nobody really works on this very much because most of the good problems were solved at the end of the 90s. Okay? Not all of them, but mostly. So this is an extremely well-behaved theory in the ultraviolet. The flip side is that the smaller I make P, the bigger this correction is. So this theory is much, much worse behaved in the infrared. And we already saw that with the correlations not dying off as fast. Okay, so let's see. G squared has units. We did that. It doesn't normalize. To make this more concrete, why don't I do an example? Just for examples are good, right? Instead of waving my hands and saying no, it doesn't renormalize, let's do an example. We come over to this simpler theory, okay, and we ask about a 4-point function. The value of this is lambda. What's the first correction? It arises from this. I'll have a momentum P being the sum of P1 and P2 coming in this direction. And we'll try to calculate that diagram. Let's see, it's lambda squared. Sorry, no, just the board was creaking. Lambda squared over 2, that's just the counting of vertices and symmetry factors. Integral d3q over 2 pi cubed, 1 over q squared p plus q squared. Feynman parameterize. We can do this. And after a little bit more work, I get an answer. Lambda squared over 2, 1 over 8p. So that's my answer. Lambda squared has different units of lambda. That got made up for by when I perform this integral. Since it's d3q over momenta to the 4th, it has to end up being 1 over momentum. The momentum scale in there is p, the momentum coming into this loop. So it had to have a 1 over p. It turns out that the x and q integrals each give me a factor of pi, which undo all these pi's, so there's actually no pi's, which is kind of weird. And the larger the momentum as you go to the ultraviolet, everything is great. Lambda squared over p. P gets bigger and bigger. This becomes a smaller and smaller relative correction. Other direction, there is a scale p where this goes to hell. And this is as big as this is, which means that the next loop will be as big as this one, and the series has gone to pieces. If I really stay with this original theory with no mass here, actually that doesn't happen, because when I wrote this, I forgot to mention that there could be masses on these lines. Notice if the theory starts out without a mass, this 3D theory has a mass. And so this p gets modified, it gets built up by some masses. So actually, if I start massless for scalar theory, the series converges, but it only converges as the square root of lambda instead of as lambda. Because if you will, for small p, this turns into a mass which is root lambda times t. And this half undoes this lambda. But there's something interesting that can happen. The standard model has a scalar, the Higgs. It has a Lagrangian that looks a lot like this. Well, covariant derivatives. But its mass squared is negative. So when I write it as a thermal thing, I have a negative mass squared at tree level, and then a positive mass squared from the loops. At very, very high temperatures, the loops win. At low temperatures, the Lagrangian wins. Somewhere in between, around 100 GeV, they cancel. And this Lagrangian has no mass. Okay? That means there can be a phase transition. Actually, it turns out that because the Higgs is heavy and it has an oddly uncouplings and so on, there isn't a phase transition for the minimal standard model, but there could have been. But it definitely shifts behavior from a symmetry broken to a massive theory as you go from low to high temperatures. And somewhere in between, it acts like a scalar with almost no mass, where the perturbation expansion fails. And you really have to solve this theory plus all the gauge degrees of freedom and everything on the lattice to know what really happens. And the only reason I can say we know that it doesn't have a phase transition is because we've done that. From perturbation theory, you can't really say anything. Okay. This theory, this has a mass. These degrees of freedom might not show up in loops. But this is massless. And you can't write a mass term for that. Same reason you can't write a mass term for Yang-Mills theory in general. And so the gauge portion of this can't get rescued by any masses. Its infrared behavior will always become large coupling even if alpha up here is 100th, that just means that you'll have a factor of 100 in scale before this theory becomes poorly behaved. So instead of exponentially far away from strong coupling behavior, you're only polynomially far away from strong coupling behavior here. Okay? And to illustrate that, and to illustrate in general how these calculations really work, let's calculate an interesting feature of a thermal field theory. Let me ask about the free energy. The free energy is T, the free energy per volume, the free energy density is minus T over volume times the log of the partition function. That's a target for calculating. And we're going to calculate this in the full four-dimensional theory with this thing, with some integrals and everything. Okay? At lowest order, there's one diagram. It looks like that. Okay, there's a fermionic diagram and there's a gauge bosonic diagram. The gauge bosonic diagram, or we could also ask what happens here in the scalar theory. All of them look basically the same. I have a T sum integral of 1/2 times the log of p squared plus m squared. Right, the log of z is given by the sum of vacuum diagrams. A propagator is when a line runs from a vertex to another vertex. What happens if the line just runs around in a circle? Well, then you get the log of the propagator, as we know, because you get the determinant. Right, if you do the path integral, you'll get a determinant of p squared plus m squared. Actually, you get the root of the determinant. 1 over the root of something, you know. 1 over the root of the determinant. The 1 over cancels this minus sign. The root gives you this half when I take the log. So that's where this came from. This is a pain to calculate. It's also terribly, critically ultraviolet divergent. That's the same as the statement that the energy density of the vacuum diverges as the 4th power of the ultraviolet cutoff. Okay? That's a problem of vacuum field theory. I'm not going to solve that problem today. But the difference between this answer in vacuum and at finite temperature should be a sensible finite quantity. And so we should subtract the vacuum version. The way I'm going to subtract the vacuum version is I'm going to do the calculation, and then at the end I'm going to see something with a T and something without a T, and I'll say, aha! This log is a pain in the butt to deal with, and so I'm going to cheat. I'm going to integrate dm squared and take an m squared derivative. That doesn't do anything, right? By integration, by, you know, fundamental theorem of calculus, that doesn't change anything. But when I take this derivative, then this becomes what I'm used to, a propagator. So now I have an integral dm squared of some integral minus integral of 1 over p squared plus m squared. That's what I want to calculate. Okay, and first I want to think about what this means. So let's rewrite this slightly. Sum over p naught equals 2 pi nt with a factor of t minus integral dp0 over 2 pi of integral d3 p over 2 pi cubed of 1 over p squared plus m squared. So the thermal contribution is the difference. My hand is not as good as the eraser. Let's try that again. the difference between using the sum and using the integral of the integral over spatial momentum of propagator. That's what I want to consider. First, I want to understand this. Here I have some function. Because of the m squared and the p vector squared, that function is somehow rather smooth. So it's some function varying somehow. Actually, I guess it looks more like this. Okay? This sum is evaluating the function here, 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 here. Whereas the integral is properly evaluating the integral. So let me slice this into pieces. I can do this integral, or I can evaluate the two boundaries and estimate it as average. I can do this integral, or I can evaluate these two boundaries and estimate it as the average. Okay? Some integrals are just one of those clumsy approximate integration solvers. That's all they are. And the difference between a boson and a fermion, besides a fermion having a minus sign here, is that the fermion evaluates at the middles of the intervals instead of the edges. So I estimate this function as the middle value instead of the average of the edge values. As you learned in some numerical methods class, or if you didn't, you're learning it now, the error you make when you do an edge point estimate and the error you make when you do a middle point estimate have opposite sign. They're of order the same size. I think they differ by a factor of 2, but they have opposite sign. That means that the error, the difference between doing the sum and integral will be opposite for fermions as it is for bosons. That's actually a good thing, because there's also this minus sign associated with fermions, because you get plus determinants instead of, or you get determinants instead of reciprocal determinants. Okay, so those two signs cancel and they both give positive contributions to the free energy. Funny enough. Can we do this these sums? Yes. And I should, just because it's cute. The sum, the t sum of 1 over p0 squared plus e squared, I'm going to name p vector squared plus m squared e squared, because it is. Okay. This sum is 1 over 2e hyperbolic cotangent of e over 2t. Incidentally, how on earth do you ever do a sum like that? Does anyone know? It's a dirty trick. It's a beautiful, dirty trick. You look at this function and you say, as an analytic function, does it have poles or singularities or something? And it does. Every time p0 is I times e, something goes wrong. So as a function of e, this thing has some singular behavior at some line of points, which is each time e is I times p0. So at 2 pi I n, it has singularities. Okay. So the answer has to have singularities at exactly the same place. Well, a sine wave has zeros at those places on the real axis. So a 1 over a sinh wave has zeros at those, has singularities at those places on the imaginary axis. So it has to be something with a hyperbolic sign downstairs. Hyperbolic sign downstairs would die exponentially. This doesn't. So I have to have a hyperbolic cosh upstairs. Okay, no, this is true. This is how you do it. Okay, and then you say, okay, but maybe I need some coefficient in front or something. And then you say, okay, well, what's the behavior up close to this pole? What's the behavior far away? And based on those, you figure out it has to have a 1 over 2e. Okay, this now has the right behavior far away, up close, and it has poles in the right places. And that is enough to completely uniquely specify a complex function. So this has to be the answer, and it is. Just a funny remark. Coth you can rewrite in the following interesting way. 1/2 plus 1 over e to the e over t minus 1. So this is just rewriting Coth. If I take t to 0, this goes away. Sorry, there. If I take t to 0, this goes away. Actually, what is this? That's the Bose-Einstein function. Huh. How'd that happen? Well, because I'm dealing with bosons at temperature. So somehow that has to come out somewhere. There it is. Okay. What's this 1/2? That is the 1/2 of the ground state of a harmonic oscillator. So if you ask, if I had a harmonic oscillator, what energy does it hold? This is the ground state energy, and this is the thermal energy. And that's exactly what this is. Okay? So in a way, this is not a super surprising answer. What happens if I do the same thing with the minus sign? If my poles are here, then what happens? Well, then I must need the cosh in the basement and the sinh on the top. And so then I get all the same stuff except a minus 1/2 plus n Fermi of e over t. So when I do the same thing for my fermions, I learned first of all that the 0-point energy of a fermionic oscillator is negative, which we knew. This is responsible for the negative and positive vacuum energies of fermionic and bosonic degrees of freedom. They both have positive thermal energies, which respectively obey Fermi and Bose statistics. Question?
Don't we also have to account for the p stat in the numerator, like with the fermion conjugators?
When you take the integral of the free, when you take the free path integral and you ask what is z, what is log z? When you ask what is z, it's the determinant of d slash. And then I can say, well, that's the square root of the determinant of d slash squared. And then I'm back to p squared. Yeah. There's a factor of 4 because of the trace of 1. But that's just counting independent particle states. So I'm not showing every single detail. I'm giving the big brush stroke picture here. Okay. Hope that's okay. Okay, so that was fun. So what do I find? I find that the free energy, after I do the integrals, is minus pi squared over 90 t to the 4th plus the vacuum contribution. Why is there a minus? Well, free energies are supposed to be negative. That's okay. The energy is positive, but the free energy is negative. The pressure is minus this, right? Times the number of degrees of freedom. That's if I integrate the Bose version. And it's times 7/8 of degrees of freedom for fermions. So as expected, I mean, this is the answer everybody knows and loves. There's no surprise. It's just that the point is that it emerges because we have these sum integrals. That's the point. Okay? That's lowest order. Lowest order, well, actually is not as bad as you'd think. But, you know, maybe you want to do better. You can do better. You can calculate corrections. At the next order, you have diagrams that look like this or like this. And these give g-squared corrections. Those are calculable. They were figured out in the early 70s. Everything's okay. And then at the next order, you have corrections which look like this. And so on. And now something funny happens. These turn out to be infrared divergent. And if I calculate this, it's more divergent. And then I panic. And then I stop panicking. I put the paper bag over my head or whatever, and I calm down, and I say, oh, but look, all that's happening is I have a propagator with a self-energy, or two self-energies, or three self-energies. And so I should sum these as some Dyson series with as many self-energies as I want. Okay? And then I find out that it looks like that, roughly speaking. What's this m squared? It's this m squared. What's the summation? It's the reduction to this three-dimensional theory. This is just the hard way of finding out that the infrared behavior is governed by a three-dimensional theory which has mass renormalizations. People manage to do this the wrong way, somehow. I make that sound too harsh. It was a great achievement at the time. So Kapusta, in NPB 148, back when NPB started with 461 in 1979, managed to resum these, and he found that the result was a g-cubed correction. Peter Arnold, in a moment of utter fanaticism, I don't know what he was trying to prove, in 1994 managed to do the basketball and Mercedes type diagrams and found g to the fourth and g to the fourth log g. Something crazy is going on here, but not that crazy. We already saw partly an explanation. So what's going on here? I start with a 4D theory. Let's just do pure glue, just to make our life a little bit simpler. So think about this four-dimensional theory. What I didn't write is you can have a constant there. The interpretation of that constant is an energy associated with empty space. I know of no lawful impediment to having such a term. I need such a term to cancel divergent vacuum contributions and make the energy of empty space 0, as we observe cosmologically up to, from the point of view of QCD, tiny corrections. But we've already seen that this turns into a 3D theory. And there's no reason this 4D constant and this 3D constant should be the same. They're not. I should have to do a matching calculation to relate them. At 1, 2, 3, 4 loops, I find contributions of g to the 0, 2, 4, 6. 4 loop sum integral, this is impossible. So to prove how incredibly cool they are, Mikulainen and Jörg Schröder did it for scalar theory, where let's see, what is it? This is the figure 8, the basketball, and I don't know, something grotesque. Yeah, that's some kind of devil worshipper diagram or something. Yeah. And they managed to do this, okay? Once you put in fermions, forget about it. Once you put in gauge interactions, nobody can do those ones. But they did up to here, which is pretty good. Okay? And so we know the value of this C3, and now we're supposed to find the free energy log of the partition function in this theory. This theory has a scale here. That scale is GT. Because this is a 3D theory, the series doesn't converge as well. So this has then g cubed, g to the 4th, g to the 5th, g to the 6th, as you go up in loop order. Actually, I could even go one further. I could integrate, since this is heavy anyway, I can integrate it out. So I can even reduce from here to a theory with only Fij plus C3 prime, a different constant. And I can think of these calculations as matchings between C3 and C3 prime. And that matching, since it's scalars and stuff, you can do to and 3 dimensions and stuff, you can do to 4 loop order, and it's done. At this order, there's logs. Why? Because this g squared, this m squared, renormalizes in 3 dimensions. So the bare contribution is m squared. The loop contribution is g squared times times a linearly divergent contribution, which then you set to 0 in ms bar. And the 2 loop contribution is g to the 4th, and g to the 4th has the right dimensions, same dimensions as g squared, as m squared, because we're in 3D. diagram can be logarithmically divergent, and it is. So this mass actually runs with scale. We calculate this as its value at the GT scale. And then it has a different value further in the infrared. And that gives rise to funny logs here. This is a matching calculation to get this coefficient, and then I have to calculate in this theory. This theory has a scale, the g squared t scale, and so one loop I get g to the 6th, at 2 loops I get g to the 6th, at 3 loops I get g to the 6th, and now I'm in trouble because at every loop order I get g to the 6th. That means that the question, what's the free energy in this theory, is non-perturbative. You have to solve this theory to find the g to the 6th term. So this is weird. At a finite power in g, I have non-perturbative information that you have to get by solving a truly non-trivial, strongly coupled gauge theory. Okay? So at temperature, the infrared behavior means that the coupling expansion actually runs out at some point and stops working. And this is actually the quantity where it runs out the very latest, where you can get the most coefficients before you get in trouble. Because fundamentally, the energy density is a very, very ultraviolet property. It's counting particles which all live in the ultraviolet. Other properties are much more infrared sensitive. So the big moral here is that, no, I guess the moral is multi-part. If the coupling is weak, and the mass scales are small compared to t, then IR is 3D. The infrared behavior acts like a three-dimensional theory. Three-dimensional theories are strange. Their ultraviolet properties are very, very good. Their infrared properties are much, much worse. For a scalar theory, the mass might save you and just barely retain a little bit of normalization. For a gauge field theory, the infrared is strong coupled, and that's just what it is. And as soon as a physical quantity is sensitive to g squared t momentum scale, or inverse, I guess it's actually best to call it a wave number. It's not actually even, it's not an energy scale, it's not a momentum scale, it's really a wave number. Then perturbation theory fails, and there's non-perturbative physics. So for this last point, I guess I give a couple of examples, and then I say that this is all we're going to do for equal time physics. The point is that there's a complete set of technology. You get a four-dimensional description with this periodic time, If your coupling is strong to begin with, you should immediately take that to the lattice and try to solve it there. If your coupling is weak, then you have a perturbative expansion, but it's complicated. It has a lot of infrared features. The right thing to do is to match to a 3D theory and try to study the 3D theory, which is a lot simpler. The 3D theory has strong coupling in the infrared. You might still need to solve it non-perturbatively. Or you might solve it in some loop expansion, but discover that the loop expansion behaves very strangely. There are a lot of properties of QCD at high temperatures we're interested in. The simplest is this kind of pressure. Or energy density. If I just very, very naively guess the energy density, I would say, well, it's an integral over momenta, the typical energy of a particle, and Bose the statistical factor, right? This energy is the same thing as P. And now I ask the question, how much do my deep infrared fields contribute to that? So first, what do temperature fields contribute to that? If P is of order T, I get here a T cubed, a T, and a 1, and I get T to the 4th. And that's right. The energy density is T to the 4th with a coefficient that's a number. Pi squared over 30. If I say, what about P of order G squared T, which is a scale where the physics becomes strongly coupled, then here I find G to the 6 T cubed, here I find G squared T, and here I find 1 over G squared is my Bose statistical function. And so I get G to the 6 T cubed, T to the 4th, sorry. That's the contribution of this deeply infrared scale. I know this deeply infrared scale is strongly coupled, so I know that I'm going to have non-perturbative contributions at this scale. And if I want to understand them, I'm going to have to solve this three-dimensional theory in some fully non-perturbative way. What about other things? Correlation lengths, for instance. So the A0 correlation length, the so-called Debye mass, Debye mass. So my Dutch friends always tell me I'm saying it wrong. We already saw that that's GT. That's sort of at the most bare obvious level. But then this physics comes in and screws this up and gives a G squared T contribution, which is non-perturbative. This we cannot calculate by hand, or it has to be determined by solving some non-trivial lattice theory. One of my favorite questions, if I have a high energy particle and it scatters, this intermediate state is space-like. And that means it turns out that this kind of, and this is a whole story, which I'm skipping beautiful details, that this kind of Euclidean methods work. So I can ask, how readily does that thing scatter? And the answer, the Euclidean methods tell me that if I exchange a momentum q, then at lowest order, That's my cross-section to scatter. Cross-sections to scatter are useless because if I scatter exchanging an infinitesimal tiny pipsqueak of energy, no one will ever know. And so what's useful is to scale this by the transfer momentum squared, which keeps track of the fact that larger scatterings are more important. Scatterings that bend you by a bigger angle matter much more than ones that don't. And so this quantity is called Q hat. We see somehow at large transfers, the transfer is screened. I have 4 Q's in the denominator. At small transfers, it's not screened. I have 2 Q's in the denominator. So the dominant scale is the GT scale. Relative to that, I can stick in Q perp equals G squared T and just evaluate this thing. And discover that for this physics, the scale of these very soft infrared divergent stuff is G squared suppressed. This will turn out to mean that essentially all dynamical features, I mean, I'm skipping a whole bunch of stuff and just telling you something instead of explaining it in detail. But later, when we try to understand the dynamics of QCD or gauge theories at weak coupling at high temperatures, we'll find that this kind of scattering is the most important thing in setting those dynamics. And this tells us that if you ever want to understand, for instance, the shear viscosity of QCD at weak coupling, at the G squared level of correction, you're going to have to solve the non-perturbative physics of the infrared. Okay, so that's just a remark. Even though your coupling may have a weak your theory may have a weak coupling, suitably deep into its infrared, there's non-perturbative physics, and it emerges at finite powers of the coupling all over the place. Okay. So that's what I wanted to tell you about today. Questions? No. Lunch? Okay.
So it's like in the 4D theory we do non-perturbative in the UV, but in this 3D it's...
So QCD, in my opinion, doesn't have non-perturbative physics in its UV. It has lots of perturbative physics that requires some resummations using tools of effective field theory, but basically perturbative. It has non-perturbative physics in the infrared. But if I go to a temperature way above that, then they become tiny corrections. Or if I go to an energy scale way above that, they become tiny corrections. But at temperature, they don't. Okay, this infrared behavior has nothing to do with the fact that QCD is confining. Okay? So I could take a conformal theory and with a weak coupling. It's well behaved on every scale. I turn on temperature, and at a scale which is G squared times that temperature, its gauge sector becomes complex, confining, non-perturbative. And we'll see in a little bit more detail why that happens. I'll give you the sort of quick answer. In each loop, it turns out that besides the usual, I mean, what a loop is calculating the effects of vacuum fluctuations. Those vacuum fluctuations are this 1/2, which we wrote earlier. And we saw that one half got turned into a 1/2 plus Boson statistics. And what's happening here is each loop, instead of a half to keep vacuum fluctuations, is a half plus n Boson to keep vacuum and thermal fluctuations. And as you go to the infrared, n Boson becomes large. And so the loop expansion breaks down. The large Boson-enhanced fluctuations all ride on top of each other and interact with each other and become strongly interacting.
Isn't that more of a problem? Because
Sorry?
we do all the calculations in the infrared. Like I'm trying to understand what we gain out of doing this thermal Euclidean 3D version of the thing. If it becomes more difficult to calculate things later.
It becomes difficult because the theory has complex behavior. It's not that our tools are failing us. It's that our tools are encountering the underlying difficulty of the theory. Don't shoot the messenger. Okay. Okay. Maybe we should have lunch.